I suppose we try to make new materials and new composites, but from the perspective of a maybe molecularly trained synthetic chemist. We're very interested in making nanoparticles, and these are usually metal-based. Sometimes they are metal, sometimes they are based on metal, so they might be metal oxides, for example. We make them for a variety of reasons. Generally, to a greater or lesser extent, our interest is what I suppose you might call catalytic. We're making, for example, nanoparticles at the moment that are heterostructured. You're combining different components within an individual nanoparticle, and one reason that you might have for doing that is to protect one part of the nanoparticle from, let's say, the wider environment, the solvent or the air. Gold is an element that exhibits plasmonic properties, but gold also obviously has a major drawback, which is it's pretty expensive. If you could render other metals, other much cheaper metals, plasmonically active, that would be potentially very beneficial. It turns out the copper is plasmonic. The reason it's not often used in plasmonic applications is because it oxidizes, so you have to protect it. And one of the ways that we're trying to do that just at the moment is by putting a protective oxide shell made from another metal around preformed copper nanoparticles. And this is, preliminary data suggests, working really well. We're looking at metal organic frameworks. This is quite collaborative work. A very sort of strong part of working in a university is the ability to collaborate. And we're working in this case with co-workers up in chemical engineering. What they generated was a method of making porous materials, metal organic frameworks, that were practically handleable. So traditionally, people have made metal organic frameworks as powders, not very easy to handle. They generated a way of making them as monoliths, so kind of centimetre scale materials. And working with them, what we've been doing is growing the monoliths around preformed nanoparticles. What that then gives you is a really robust way of immobilizing nanoparticles. So something you might be concerned about if you're trying to apply a nanoparticle catalytically is how do you recover it? It might be expensive to recover, or if you lose it into the wider environment, there could be health and safety implications of that. If you can really, really robustly immobilize it, using, for example, a monolith, then perhaps there are new avenues there for applying nanoparticles in ways that are not currently very easy to do. In academia, you've got relative freedom still, so whilst applications are important, you can still pursue ideas that might come to fruition in maybe 10 years rather than 2 years or 18 months. Also, I think being in a university, that adds a certain vibrancy that perhaps you don't get in an industrial setting, because you've got new people constantly arriving, new students constantly arriving. They'll bring new ideas, new energy often, and they can think things that even 5 years ago nobody working in the area would have thought. We're focused on a range of applications in our work. Something we're very interested in is photocatalysis. We work with collaborators around the world on pollution abatement, and a very important method of pollution abatement involves harnessing the sun's energy to promote chemical reactions. So often what you want are photoactive nanoparticles that can promote, for example, the degradation of a polluting molecule. A lot of interest out there on gas storage. People talk about the hydrogen economy, so storing hydrogen in porous materials, storing methane also in porous materials, or carbon capture. So the kind of metal organic frameworks that we look at the moment, just as they can store gases like hydrogen, they're very good at storing carbon dioxide. I think it was a bit of a culture shock, yes, when I first arrived in Cambridge. I wasn't the very first person in my family to go to university, but I was certainly amongst the first. I don't come from a family that I think you would traditionally have thought of as producing university graduates since way back when. I went for State Comprehensive, did my first degree at the University of Kent. I suppose thought of somewhere like Cambridge is probably not somewhere I would get into, and I can, I have quite vivid recollection to this day of sort of asking my tutor back in Kent, well, should I even bother applying for a PhD there? But, fortunately, they said yes, go for it. So it was, yes, it was different, I think, when I first got here, but I think once you actually start talking to people, you realise that there's a lot more people who are more down to earth than perhaps you imagined. There aren't any shortcuts. It still requires hard work, application, and you've got to put in the hours, but providing you do, if you have the ability, then it will be recognised.